Hello, this is the next video on a playlist that I'm calling General Linear Models Design of Experiments, and this is part 3 of a little mini-series on split plot designs. And here we're going to look at perpendicular projection matrices on the different column spaces of these design matrices. Now in part 1 and 2 we looked at the split plot completely randomized design. That's where the first factor is randomized using the CRD design. So factor 1, and then the second one, the split plot's always a randomized complete block design. We also looked at where the first piece of the split plot was a randomized complete block, and then we had to introduce a block effect. Now in the book Montgomery, the problem or the illustration they do is what's called the full model. So it's actually from here to here we're adding block effect, and so from here to here we're adding an interaction effect between alpha and beta, and an interaction effect between beta and gamma. And then the three-way interaction, alpha, beta, gamma. Notice there's no error terms, and that's because there's a parameter for every observation. So it's way over parameterized. But in Montgomery, they illustrate this, so we are too. Now to follow up on part 2, looking at the design matrices, since we're introducing 2 new little subspaces, we're going to look at the design matrices associated with that. And I'm not really going to cover more than that, except for that it's this fashion, and this will come up more in later videos, especially the R illustration. Now the perpendicular projection matrices onto each of these column spaces associated with mu or actually we can use this one, alpha, beta. Each one of these we're going to look at. And to create the perpendicular projection matrix, we take the column space, times its transpose times it, inverse, 1 transpose. Anyway, so this creates the perpendicular projection matrix onto the column space of 1s, and we've always called it J. And it creates this square matrix that's T by R by M, or T times R times M. T is the number of treatments, R is the number of the replications if we're doing the split plot design or the completely randomized design, or it's the number of blocks in the SPRCD design. M is the number of levels for factor B, and this is it. And so it's a square matrix of this. Now M alpha is the perpendicular projection matrix on the column space of X alpha, and this is the form of it, which then this piece is just 1 over Rm, and then those here, and that creates what's called a block diagonal matrix. M beta is this. Now we're going kind of fast. I mean, I've derived these in great detail in a few of the earlier videos, and so I'm going to skip them, but I encourage you to go through these and make sure that makes sense to you. Then this what creates a block diagonal. So it's block diagonal, so it's blocks across the matrix, but each block is block diagonal. And then M alpha beta, sometimes we call it MW if we're in the split plot CRD design. It's this, which is a block diagonal. Then M alpha, again, you use the column space of X gamma. I said alpha, but it's M gamma. And it ends up being what's called a block diagonal of the identity matrix. M alpha, and again, you multiply that column space and you create a perpendicular projection matrix, and it ends up being block diagonal, but each diagonal is a block of IM. Now, one thing to note that each of these, did I mention that? Oh yeah. So every one of these perpendicular projection matrices, TRM by TRM. And so it's a big fat matrix that we're creating that is these perpendicular projection matrices. And what's crazy, all of these derivations we're going to use in the R statistical software in part 10, and all these crazy matrices then multiplied together, it's going to equal exactly what R puts out. And to me, I find that quite fascinating. So M beta gamma is you take the column space of X beta gamma and it creates this design. It's a block matrix of identities. Now the three-way interaction term, so M alpha beta gamma is just the identity matrix. Now a few of these properties, when you multiply them together, and this is going to come up later in videos, what does it look like? What do they look like? So when you multiply M alpha beta with M alpha gamma, notice that when you left multiply something, it projects it into this column space. But notice that alpha column space is part of this interaction space. So it already, and alpha is part of this, so it sort of already lives in here. So it projects it back into it, and it creates this M alpha matrix, right? Because it's common in both of them. And to do this, and I encourage you to go through the proof, if we look at the product of these two, and then put in their structure, it's block diagonal of this matrix of all ones, square matrix of all ones, and this is block diagonal block matrix. So I try to write this out. So this one, I take the M and the R and put it out front. And this is block diagonal of this, so it goes down the side. Now this is block diagonal of this, so each diagonal is this matrix, right? It's block IM. And then it's block diagonal with this going down the diagonal. And I didn't write it out, but I'm going to just do one here. So when you take this times this, you get U back, right? But then when you take it times the next I, you get it back. And so there's R of those. And that's why this ends up being an R times M matrix of all ones, because when you do that multiplication. So then it becomes just a block diagonal of RM, and that ends up being this one right here, right? So we just produce that. But it's easier for me to think about there's an alpha common in both of those, so it makes an M alpha. And the same way here, so M, the perpendicular projection matrix on the column space of alpha gamma, and then the perpendicular projection matrix onto beta gamma. When those multiply together, you have a gamma that's common, so it projects it back into that. So that's what we get here. Alpha M alpha beta, M beta gamma, there's a beta common. Now here, M alpha beta and M gamma, it's only that the column space of ones is common in both of that. So that's the perpendicular projection matrix on the column space of ones. Now, the 5 and 6 we'll use in a later video. But when you multiply this out, so M times J, so the M cancels with one of the M's in this and creates this. And then this times that, you just get a rectangular matrix of all ones. But then this can be separated out into X gamma, and then this square matrix of all ones. And this actually will play a part in proving that the ordinary least squares estimates are blues. And we'll need this property, and actually this one up here too. When we multiply M times this perpendicular projection matrix times this perpendicular projection matrix times the column space of alpha gamma. Now, this times that, it's in the column space, so you just get it back. So this, or these two make that. Oh, we could have gone that way, but here, for some reason I did that. Since this is alpha, I put alpha. Now, this is a block diagonal of this square matrix times that, and then multiplied together you get a block diagonal of this rectangular matrix, and then this can be separated back out into. Now, I went fast here, but make sure that's right in your mind. Now, these mean vectors are also important when we're doing estimable functions. So the grand mean vector is j times y, which is this. And I want to actually show you this here. So when we look at the column space of all ones, And we're pre-multiplying y times, pre-multiplying y times j. That j shoves it down into the column space of this. So we better get a constant vector, a multiple of it. And that's what we do. So this is a constant vector times a grand mean. And when we look at the mean vector for alpha, y alpha bar, so we take y and pre-multiply it by the perpendicular projection matrix on the M alpha. And notice that it's going to shove it into this column space. So we're going to have a constant, like a multiple, or a constant times that, a constant times that, and a constant times that. But the way that it's multiplied out, that constant is the mean for treatment 1, and that's that one vector, you know, that is here. Now that one ends up the second one, so it's going to be the mean for treatment 2 times that, and then all the way down to the mean for treatment t. Now we'll do 3 more mean vectors, and then we'll call our quits for this. The y beta bar, so the mean for beta is m beta y. So m beta projects it into the column space of x beta. And so if we look at that, which is here, so we're going to have multiples here, but then it's going to repeat. It's going to be the same, and then it's going to repeat that. And that's what we get, right? So each of these little 1 vectors gets a mean. So it's the mean for block 1, block 2, all the way to block R. And that's what we just got here. But then it repeats, you know, t times. There's t treatments. And so that's what we get here. And so in the same way for y gamma or bar, is that these are going to, you know, it projects it into that column space. So the column space of gamma is this. So it's the identity matrix. So there's m of them the same, but then this is it's repeated like lots of times. Notice that every one of these, you know, this is the identity matrix. You go to 1, a 1, a 1, a 1. So there's no vector like these. So look what we get here. So it's just a number. So it's the mean of level 1 for factor beta, you know, or the second factor, the mean for the nth level of factor, you know, the second factor. And it's just a number. But then it's repeated tr times. And that's because it has to be in the structure of this column space. Right? That's what it says it does. And then this last one is the mean for alpha gamma. So we take the perpendicular projection matrix onto the alpha gamma space, you know, pre-multiply y, and then we get this mean vector. But it has to be in the structure of this column space. So notice that we're going to get a lot of repeats, and then that's going to repeat t times. So, right? So then, so that we get repeats, and then, anyway, so that's what we get here. So the mean for 1, 1, you know, 1, 2, 1 m, and then that repeats r times, and then it goes to y21, y22, y, or, you know, dot m. Anyway, so it's repeated that many times because it has to be in the same structure as this. Well, anyway, that's all I have for this video. Hope you enjoyed that. I sure did. Please like it and subscribe so you don't miss the next one. Thanks. Bye.